So guys, you only have landed up with this to this topic that today we'll be discussing. It's a very hot topic, okay? The low power design in a VLSI. Earlier, if you go back in the era around 50, 60 years, this topic was not at all there. This has been coming up from the past 20, 30 years with the evolutions of laptops and your mobile phones. So what all the topics that I'll be covering in this is the first is every time when you understand a topic, okay, first understand why was the need for the lower power design, the need, the purpose, the objective. Until and unless you're clear about it, you won't be able to understand the topic clearly. That's not only with respect to this topic. I'm saying anything. If you're studying it, you'll let to know that what was the need, why was it being designed, what made someone to land up to the conclusion that there is a requirement of low power in our designs. Okay, so first we'll understand what are the needs for the low power design in our VLSI sector. The next is when you come up to the conclusion that, okay, we need this technology, we need something like this. The second is, what's the solution for this? What's the strategy to apply for this? Correct? So the second thing which we'll be discussing will be the techniques on how to implement all these low power designs. Okay. Third is the most important thing that my agenda around this lecture would be like the low power design cells. When you have comes to a strategy, right? For example, that I'll be using this strategy. In VLSI, everything works around with the respect to cells, right? So now we do have some special kind of cells to implement these techniques. So the major part of this entire lecture would be something, this communication would be like, what are the major low power design cells in the VLSI? I may not be covering every cells in depth, but yeah, I'll get you know the overview of what are the cells in the designs which help us to achieve these techniques. And finally, we'll be looking into the example of how this low power design cells are being used in the VLSI circuits. So guys, are you ready for it?
Yes, ma'am.
Correct? And please let it be a two-way discussion. I don't want it to be a one-way, correct?
Yes,
Okay.
ma'am.
Yes.
So the first topic as it stated is the need of low power design. Now, let me, for example, now as you said, right, when we are going into market for looking up any battery powered device, whether it be a laptop, whether it will be a mobile phone, iPad, anything else, correct? You look at something which is the most important factor is the battery life. Okay, that for example, now let us conclude. Let us take it as a real time example. Okay, if now for example, um, anyone, what did you have for breakfast today? Anyone? Guys, you had the breakfast?
Idli, ma'am.
I had idli and dosa.
Idli and dosa, sambar chutney, correct? You had it, correct? So now, when you had this thing, now I see that out of 10 to 15, I'm not sure how many members are there, out of 10 to 15 folks, only one person has the energy. Rest, everybody, I think they ate only, I think, sushi or something on there. They don't are not left with the energy, correct? Guys, I want everyone to speak it up. This is not something like
Yes,
you are
ma'am.
appearing for an interview or something you're scared of. Okay, I don't know who you are, you don't know who I am, correct? So speak it
Yes,
up.
ma'am.
So thing is like now one the person had idli sambar. Now this person might have ate it around, let's assume that his mom has prepared this yummy breakfast around 10 a.m. Now from 10 a.m. it's now around approximately 1 p.m. correct? So now I look at it that the person still has the energy left with him. Correct? He's able to cope up with me. He's delivering the responses to me. While the rest, everyone's battery, I think, has been lost around at 11 a.m. only. Correct? I think so. So the thing is, I don't want this kind of people to be in my lectures, okay? You have to be energetic. You have to have a long-term power. Whenever there are going to be lectures, it has to be a stretch of 1 hour, 2 hours, right? So your energy or your battery should not drain it up, correct? So the most important thing similarly happens in the low power designs. Low power or anything in the semiconductor, it always relates to your normal your life. Don't take it something that's a very different thing. Okay. So the first thing why you have to there was a need for the low power design is the answer is it should have a higher what our designs or what our machine should have.
Power dissipation or heat.
Not the heat can be something which can be covered up under an umbrella, but the first thing is your battery life. correct? You want your
Yes.
battery life to be higher. Everything else may fall under this bucket, but the main important thing that you want is your battery life should be higher, correct?
Yes.
So let me say that the first requirement that we came up to the conclusion that we need lower power is the battery life. Until and unless we have a higher battery life, there is no use of it, right? Otherwise, we would have still sticked up to the something as continuous charging supply ports, right? We wanted that whatever battery we have in our design, whatever mAh power it has, it should for a long duration, you'll be able to run it, right? Now, for example, the person who had the breakfast, its energy died in within 2 hours. Are you okay to, for example, if such people are participating in a game, would you like to have such contestants with you? Bala, would you like somebody who had a sushi and his or her energy died within an hour? Will you
No,
take
ma'am.
that person for
No.
participating in any game?
No.
No, correct? Because you need someone who has a larger battery life, correct?
Yes, ma'am.
Correct. Now
Yes,
somebody,
ma'am.
great. Okay, somebody, now the second thing is, now somebody over here told me something about as a heat. See,
Ma'am,
something, anybody said something? Okay. So somebody stated like there is something which is a heat control, correct? Now, for example, I'll tell you something which is not relevant for the today, but if you might have heard or gone through it like around 10-15 years back, if I'll say, if you would have heard the feedback of the Samsung phone, I'm not sure how many would have Samsung phone. The Samsung phone had it's not currently, I'm saying it's around 10-15 years back that they used to get heat up a lot. Okay. Now what it happens is whenever there is nothing but whenever your this is something whenever your heat dissipation happens, the battery life reduces. These are indirectly correlated to each other. So in order to have a longer battery life, your power dissipation has to be reduced, correct?
Yes.
yes,
Correct.
ma'am.
So what happens is this heat dissipation directly is something which is not related to the very constant, it doesn't affect your constant performance. It affects in the long run. Okay. What happens is, I'm not sure if you are aware, there is a terminology in VLSI which is called as EM, which stands for electromigration. Okay, if I have to explain you in a very layman language, what happens is electromigration affects the reliability of your device. If you check that, if you have seen in your curriculum or something that under the reliability checks, there comes as a check as EM check. Okay, what happens is if you look at the bookish definition of something that due to the continuous flow of current, it's mainly related to the current density that whenever the current continuous current flow is nothing but the electrons. What happens is that they take off some metal ions and displaces it from its original positions. Okay. And then it deposits it somewhere, and from somewhere it has eroded it. So wherever it keeps on depositing those charges, there comes a thing which is creates in VLSI, we call it as short. Okay. And from wherever it erodes that metal ions, it keeps on creating a void or a hillock. It is termed as hillock. If you didn't understood it, let me give you a very simple layman example. Okay. Consider a water pipe. Okay. Inside that water pipe, the water is flowing with a very high energy, very high speed, and a very high energy. Okay. In the initial stages, it will be very fine. For years and years, it's very good. The water pressure is the same, but what happens that after 10 to 15 years, what happens is, let's assume that it's a plastic pipe. Okay. Now what happens that when it flows with such a high pressure, some of the particles of this plastic pipe will get eroded because of it, will get removed from it. Okay. And whenever it keeps on floating somewhere, it will keep on depositing it. Okay. Now when you keep on depositing it, um, over here only I can note it. Okay. Let's say this is a pipe. Okay. Now, for example, from this area, it has taken up this ions of this plastic pieces. And let's say that it kept on depositing over here. From here also it kept on removing and kept on depositing over here. So when you keep on depositing over here, what happens is the pressure with which this water was flowing, okay, the diameter of your pipe have reduced, correct? And some point will happen that if it keeps on depositing it, this entire thing will get clogged or blocked and your water can never flow. Okay, before this, what it can happen, it once this is opened up, right? There is no particles over here. Okay, so this will create an open over here. What you call it as open in terms of VLSI, it is called as open, and this is called as short. This is even called a open or void. Okay, and this is called as hillock. Because it kinds of like the upper layer, why it's called as hillock is there are two hills which have locked each other. So this is the terminology which is called as hillock. So same happens with the wires as well, okay? Because everything in your VLSI is the electrons flow, current, voltage, right? So if the current is unable to flow, there is no use because your circuit is not getting anything. So in order to have a good reliability, you need something as lower EM. And the lower EM can be achieved with a mechanism for heat controlling. There are cooling pads in your, even if you look at your laptops, if you open up your motherboard, there are sometimes a cooling pad in your designs, okay? Now there are new phones which are being involved for even they have outer external fans in it. So the second point which I wanted to showcase is the reason why we need the low power design, right? I can erase it. Can I erase it? I have. Sure. Okay, so the second mechanism, the second important aspect for which we discovered that we need low power design is heat control. Okay, guys, you're up with me,
Yes,
right?
ma'am.
You have slept,
Yes,
correct?
ma'am.
Guys, at least I need 4-5 yes.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah.
Yes, ma'am. Yes, ma'am.
Okay, understood. Thank you so much. Okay, now, guys, since today it's an Independence Day, right? I have a rally which has to go for a 5 kilometer marathon, and you have to hold the Tiranga, that is our national flag, in our hand and run a 5 kilometer marathon. Is anybody ready to participate? Guys, I
Yes,
leave
ma'am.
Mumbai. Okay. How many are from Mumbai are there over here? Anybody from Mumbai? No one? Anyone
ma'am.
from Bangalore?
Bangalore, yes, ma'am.
How many folks are there from Bangalore? At least I need 2 to 3 folks.
I am one, ma'am.
You're the one. Anyone else?
I'm two, ma'am.
You're the second one. Okay, now both of you. Now you guys, I'll have
Yes,
to
ma'am.
select the one who is performing best, and I'll be representing the marathon in the year 2028. Okay. I'm a good
Okay.
athlete as well for your information. Okay.
Okay.
So now you two guys have to participate in my this Tiranga rally. Okay. Carrying this. Now it's a 5 kilometer marathon. Okay. Now, as you know, we are in India. Before you start this race, I'll give you a glucose biscuit. You know Parle-G, correct?
Yes,
You
yes,
would
ma'am.
have got when you even attended your school's annual day or your school's Independence Day, you would have got this, right? Eclairs and kind of Parle-G.
Yes,
So
ma'am.
I'm
Yes,
Yes, ma'am.
ma'am.
Parle-G, and for energy drink, I'm giving you Fruity. Both of the candidates, okay? One is one is Upendra, and other person, who is it? May I know his name,
Venu.
please? Venu?
Yes, ma'am.
Okay, so I'm giving one packet of Parle-G
Parle-G.
and Fruity to Venu and one to Upendra. And okay, now the marathon has started. Now what happens that after running for around, let's say, 2.5 kilometer, Venu's energy is all gone. Okay, Venu is completely tired, while the Upendra is still running. Now, for Venu to have the energy again back, what should I do?
Giving energy, ma'am.
Giving energy. So what is the source of
You
energy I
should
have?
bring energy drink.
Parle-G. Parle-G and
Parle-G,
protein.
correct?
Food.
So I have to give him one packet of Parle-G and one Fruity again, correct?
Yes, ma'am.
So I gave him another packet of Parle-G and Fruity again, so that he covers the next 2.5 kilometer again. Correct? I want both of you to complete this marathon, okay?
Yes, ma'am.
Now just tell me, in order to complete a 5 kilometer marathon, Upendra took 10 rupees Parle-G biscuit package and a 10 rupees Fruity. Correct? So it cost me for Upendra, how much did it cost for me? 20 rupees,
20.
right?
Rupees.
But while Venu costed me how much rupees?
40.
Double.
40 rupees, correct?
Yes, ma'am.
Now, the same things comes in the real life. that whom should I select when I am going for appearing for a marathon in the year 2028? Should I select Venu or should I select Upendra?
Upendra, ma'am.
Upendra. Why? Because
Because
Low cost.
because he's
low
saving
cost and
cost, right?
Yes,
Yes.
Along
Power
with
consumption come, ma'am.
also performance, ma'am.
yeah, because he along with the performance, see the performance is also one thing, and second is everyone
no,
whenever you go to the market to buy something, you want like okay within if I pay less and a good quality, your main intention is also to pay less, right?
Yes,
Yes.
ma'am.
So
Yes,
thing
ma'am.
is, why should I buy someone for my marathon when he needs 40 rupees and somebody whom I'm getting and so only can cover up the race in 20 rupees? Correct. Also, along with this, what happens is this Upendra, he ate one packet of biscuit and one fruity. He had created something as a byproduct as a plastic waste, right? Which are non-disposable. While the Venu has created four such waste, correct?
Yes, ma'am.
So this is
Hmm.
also not good for the environment. So the next thing that comes into the when I correlate this real life example with the low power design, something that the third comes is my cost and sustainability. Correct?
Yes, ma'am.
I want my designs to have a minimum cost and a higher sustainability, and that I can achieve with these techniques which are achievable through the low powers. Correct, guys? Understood?
Yes, ma'am.
yes,
Now
ma'am.
I have your energy up.
Yes, ma'am.
Yes, ma'am. I still out of
No,
10,
ma'am.
15 folks, I can only hear yes, no, only from one or two folks. Where are the rest? Guys, you're there or not?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Very. Okay, I think a lot of folks from here, I think I especially are. How many of you are Gen Zs, I believe? Correct? I think everyone is born after 1998 or something. All of them are Gen Zs. And you know that Gen Zs are good in a lot of things, but I believe that from today's lecture that the kind of energy that the Gen Zs have is not up to the mark. Guys, I am millennial. I am very older to you. I'm still delivering the lecture. I have to go to the gym after this. Then I have to participate in this rally as well. Then I have to go in the evening to the dance class. I have to finish off my office work as well. How much energy I have and how much energy do you guys have? Just to answer and response, you don't have the energy.
Ma'am, your
Gen Z guys,
timetable is fixed.
huh? Anybody said anything? So now the thing is, what I believe is the Gen Z people, without doing anything, are getting lazy. Their energy keeps on draining. Okay. And that's the next concept, which is related to particularly to the Gen Z. Okay, now the next concept is, have you heard about the tech nodes? If you work with the industry standard, there is something which is called as technology nodes, which you would have heard as 180 nanometer, 45 nanometer. Now, currently, which is working upon, we are working, if you look at the Intel Foundry, it works with 14A, which is 1.4 nanometer, which is approximately considered as 2 nanometer. TSMC is also working with it. TSMC has 3 nanometer. Have you heard upon it, this, guys? I should not be like
Yes,
speaking
ma'am.
something which you're
Yes,
not.
ma'am.
Yes, ma'am.
Okay. So we have evolved from 180 nanometer to like approximately like within next 3-4 years, we will be in 1 nanometer or something, right? So imagine this is, I won't go deep down for this lecture, like what is this tech nodes, how are they related to your channel gates and everything. This is complete CMOS related semiconductor physics. I just wanted to know that you're aware about this. So what happens is as and when you keep on coming to the lower nodes, right?
Hmm.
There is a concept of something as which becomes prominent. This concept has already been there even in 180 nanometer or something, but the concept which comes now is similar to something which Gen Z have, that without doing anything they are draining up their energy, they don't have their energy left with them, and that something is the leakage power. This has become prominent only in the advanced nodes, not in the earlier frame, but only in the advanced nodes. This is something like there, like even if the device is not working or is not in the functional mode, there is something which keeps on dissipating in the form of power itself, and that's called as a leakage power. Okay, so in order to even address these kind of power, there comes up the concept of how to handle it through the low power designs. Okay, fine. So
Yes,
guys,
ma'am.
out of
ma'am.
all these things,
Yes, ma'am.
now sum
Fine.
it up. For example, now what do you want out of this? Now let's sum of all this for whatever is the need. In short, what do we need in to have a good low power design? Anyone? What
Leakage,
do you think you need?
battery life, ma'am.
You need a good battery life, something which is running fast as well, something which is very cool in itself. It does not require a lot of heating control mechanism because it itself is in a cool and within your budget and is not even leakier, correct?
Yes, ma'am.
And
Yes,
this is the
ma'am.
requirement not only by you or me, this is the requirement by the complete market. Okay. The entire world needs something which is very fast. It has a good battery life. It's sustainable. Uh, it's cost efficient. It does not even if it's not functioning or it's kept in a sleep mode, it should not be leakier. Correct,
Yes, ma'am.
guys? Are you up with me?
Yes, ma'am.
Yes, ma'am.
Okay. So now, hey guys, how can I erase this? I'm not sure. Does this annotation get? I always use a different kind of a board to appear for this. Okay, now you guys can see what's the heading of this
Type of power dissipation.
types
Power
of power
dissipation.
dissipation, correct? I think
Yes,
this
ma'am.
you would have studied even in your BTech and everything. This is not something new. I just wanted to cover it up because it has a link or it's kind of a prerequisite for the topic which I want to cover it up. So guys, tell me what's the different type of power dissipation?
Static
Static and dynamic, ma'am.
Yeah,
Static
the
and-
major category is static and dynamic. Okay. Now, if you look at it, out of these two factors, if you go and look at the different types of paper submissions and everything, the study has found out that the majority of the power dissipation out of these two happens because of the dynamic power dissipation. These two itself are a very vast topic. I'm not going to explain you what is dynamic power dissipation, its types and everything. I just wanted to let you know that out of two, which is dynamic and static, the dynamic ones contributes to almost 60 to 70% of the dissipation within the complete chip, while the static power dissipation contribute roughly around to 30 to 40%. Okay. See, now the aim is not only to reduce the dynamic power, but we have to even reduce the static power. But now, for example, the thing which is contributing more, if you reduce it, this will help you, right? So out of this two, if we
Yes.
have to select which to reduce, the major factor that the people have looked upon is to reduce the dynamic power, correct?
Yes, ma'am.
Okay, now theoretically, you guys know what's the dynamic power. How, you know, within dynamic power also there are two types of different power dissipations.
Yes, ma'am.
What are those?
Oh,
Somebody? Guys, you have not visited the power dissipation or your power has already been dissipated. Guys, there is something as switching power and something as short circuit power.
Yes, ma'am.
Okay, and while when you go into the static power dissipation, there is something called as leakage power dissipation, which I said that the leakage power, that the Gen Zs are leaky, right?
Yes, ma'am.
Guys, please answer it. I
ma'am.
said that this has to be a two-way communication. We are not like, I am the one sending you a envelope and then it will reach you after 2 days and then you'll reply me. I'm not kabutar ja, correct? Be
okay,
two-way.
ma'am.
Okay. Now, the first is the dynamic power dissipation, while the second one is the static power dissipation, correct?
Yes, ma'am.
Now,
Yes, ma'am.
Yes,
I have
ma'am.
written up a formula which is calculated by the scientists and everyone, that the switching power dissipation is equal to alpha C VDD square F. Okay. Now,
Ma'am, what?
everyone knows like what is the significance, or at least not the significance. Everyone knows like what of this each individuality represents.
Yes, ma'am.
Yes.
Okay, can you tell me what does this alpha stands for?
It's basically switching
Activity factor.
Correct.
Switching
Alpha
activity.
stands for activity factor. What does C load stands for?
Load
Capacity.
capacity.
Capacitance, ma'am.
Okay, it stands for the
Load
capacity. The
capacitance.
load capacitance. Correct. Now, what is VDD?
Voltage and
Volt.
frequency.
Volt.
What? I can't hear anyone.
Dissipated.
Power supply VDD.
It's the direct power supply to the cell, whatever it's being
Yeah,
used, right?
it's
So
a direct.
that's the
Yeah,
power supply.
it's the V normally in guys. We are in VLSI. V stands for voltage, correct?
Yes, ma'am.
Okay. So this is the direct supply voltage which we apply to the device, to the cell. When you have drawn your famous CMOS circuit at the top, tuck, 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 PMOS, and then you draw NMOS, and at the top, what do you connect? You connect the
VDD.
power supply, right? VDD, ground, correct? So
Ma'am,
VDD
yes,
is
ma'am.
what it is. It's your
Yes, ma'am.
supply voltage. Okay, and what is F?
Frequency.
Frequency, the frequency at which a
Operating
circuit
frequency.
operates, right?
Clock frequency.
Correct?
Yes,
Yes,
ma'am.
ma'am.
Now, if I ask any layman language or somebody, like if you have to reduce your switching power dissipation, what will you do? Just look at this random whatever expression I have given and just let me know if I have to reduce switching power, what should I do?
Reduce VDD.
Reduce VDD. Okay. Anyone
Uh,
else?
We can play with the activity factor.
Frequency.
Play with the activity factor.
Frequency.
Somebody's playing with the frequency. Okay.
Lower capacitance.
Somebody play with load capacitance. Correct. Because all four are there. If I reduce alpha, this will reduce my P. If I reduce my load capacitance, this will also reduce my P. If I reduce my VDD, this will also reduce my dissipation. And if I reduce my frequency also, this will reduce my power dissipation. Now, same thing the scientists have done. They have not taken anything out of like magical something or they have started playing it. They started playing with individual factors and this led them to develop the second topic which was there was like different techniques to reduce the power dissipation, right? So if you if you reduce individual thing, individual techniques got invented. Correct?
Yes, ma'am.
Okay, but just if you look at this, there is one factor which can help you drastically reduce the switching power. And what would be that? Just from the formula, it's visible.
Uh, Power supply.
Power supply. Why? Why did you land
It
up
is
to this?
aware
Hmm?
because it's at the square, right? So directly it affects the
Because
factor of square.
yeah, it does not have a direct linear relationship. It's the square of something. For example, if earlier my VDD was around 2 volt, okay. So the let's say other all factors are 1. So VDD was 2 volts. So this has came to 4. 4 watt of dissipation. But if I reduce it to around let's 1 watt. So it came down to 1/4, correct? Because
Yes.
it's
Yes, ma'am.
it's not having a linear relationship. It came to something which is as the square of VDD. Okay. Now, the next thing which comes is with individually out of this, all this alpha, C load, VDD, and frequency, if I keep on reducing it, how it helps me to achieve the different techniques. So that's the third topic. Okay. What
Yes,
are the
ma'am.
different techniques for the low power dissipation? Okay. Now, over here, I have mentioned 5 different techniques. I'll not be
Yes.
going in depth because I have said like this is not the main agenda of this. The main agenda is the low power cells, but I'll try to explain you what are the different techniques which are there in the market with which we have implemented so many low power designs in our SOCs or chiplets. Okay, the first thing is okay. Now when you looked at that formula, okay, alpha F CVDD square. Okay, the first one was alpha, okay, which was nothing but your switching activity, correct?
Yes, ma'am.
Okay, you guys know, I'm not sure if you're really aware of the real term, like how does this analogy relate to it? It's like switching factor is nothing that how many times within a clock period, within a clock cycle, your data keeps on changing. Okay, okay, let me assume. Everyone knows what is flop, what is latch. Okay, guys, this I don't need to explain, correct? You're a,
Yes, ma'am.
okay.
We're aware of.
Now, if I'm saying I'm having a flop, okay. Now the flop, there are 2 different types of flops, right? One is positive edge triggered and other is negative edge triggered, correct? This edge triggered means, what does it means? That, can anybody answer what does this edge trigger, positive edge trigger, negative edge trigger, when you call it, what does it mean?
Ma'am, it deals with 0.
It deals with 0 or it deals with rising and falling edge? What is
Rising edge. If the
edge, right?
pause.
They are not flops and latches are something different, right? Latch works on level. Flop
Left, right.
works on edges, correct? This is the main difference. You would
Yes.
have written 5 marks answer
Flop
difference
works
between
on
flops
the
and
what?
latch, guys.
Mm.
Correct?
Yes, ma'am.
Yes.
Okay. So, but what's actually when you say this, okay, this is positive edge triggered, negative edge triggered, what is triggered? What is
Actually,
it?
what
A
Look, it is
voltage level.
the voltage value from 0 to 1. So at that event, your flop is actually passing your data,
Data.
or
Which,
the data
what
is
is,
transparent.
whose edge this is?
Sorry?
Clock
You're
edge.
Yes,
saying
ma'am. What?
whose edge it is. You're saying that the when the signal is rising, it's going from 0 to 1. Which signal is going this?
Clock
It's a
signal.
clock.
Clock, correct. Okay. This alpha is always related to the clock, which is the activity, switching activity factor, correct? Now, example, what happens that you guys have seen clock signal, how to draw it, right? I don't need to draw and showcase and ruin my board. You know, right? If I say you there is a 1 ns clock signal and which is of 50% duty cycle, you know, right?
Yes, ma'am.
Positive side, you high width you will give 0.5 and low level you will give 0.5, correct? Everyone knows, right? How to draw a clock signal,
Yes, ma'am. Yes, ma'am.
correct? Now what happens is when see in a real world example, there are a lot of registers and lot of flops in your designs. Okay. So now this more than let's say in our understanding, there are 1 lakh of flops in your design. And then I'm only considering, let's say only one clock is going through all of this. Okay. Now, whenever the clocks goes, every time when there is a rising edge, this flop opens up and whatever the data signal is coming, it allows to pass through it. Okay.
Mm.
Now, when I am an architecture perspective from the design, I know, for example, that for example, let's consider that for 10 clock cycles, my data is not going to change at all. Okay. My data is like, I'll be passing on 1. Okay, through the entire this 10 clock cycles. Is there a use that I every time pass on this cycle clock cycle? Every time when it will hit a rising edge, my flop will get triggered. It will use some energy. It will open up, transfer the data. But the data which is being transferred is again 1, correct?
Yes, ma'am.
So what happens is that this people came with a conclusion that when I'm not having any data change, why let me pass on the clock itself? Why shouldn't I block this clock? Correct? Because it's taking a lot of energy. Your clock generator circuit has to generate this clock. Your register has to open up, pass this. It's wasting the time. Along with this, the major focus is wasting up your energy, correct? You don't
Yes,
want
ma'am.
it. So they came up with the first technique, which is called as clock gating. Okay. The word gator is, see, in VLSI field, whenever you say something as gating, it is like you can turn it on, off. It's kind of a gate which you can open and close, correct? So
Yes,
this
ma'am.
is something which is a technique which is being developed so that you can reduce your switching activity. If you reduce the switching activity, this will help you with reducing this will help your dynamic power, correct?
Yes, ma'am.
Understood? There is a different you would know that to implement this, there is a kind of cell which is called as ICG cell or CGC cell, which is called as integrated clock gating cell, or they call it as clock gator cell. Okay, this is designed. This is not something which I'll be going into deep. There are different low power cells which are related to UPF. I'm not going with this design, but I'm just saying you that there are different cells which are being even designed to implement this clock gating. Okay. Now, the second thing is, for example, if you want to save the power, why not, let's say, for example, now let's say that today when your mom went to kitchen to prepare your breakfast. Okay, she normally prepares the breakfast between 9 a.m. to 10 a.m. Okay, now she goes and prepare the breakfast in the kitchen. Now she knows that during this time period, I don't need to be in the hall. I don't need to turn on the TV. So she can turn off the TV. She can turn off the lights and fans of the halls, correct?
Yes,
When she
ma'am.
knows that between 9 to 10, I'll be in the kitchen. Now she knows that once this is prepared from 10:30 to 11:30, I'll be in the hall watching up a TV or some show, correct? So then she will turn off the lights and fans of the kitchen. She'll turn off the lights and fans of she might turn chimney off, right? Okay. What is she doing?
Saving power.
Power
Saving power,
gating.
correct? So the same thing happens over here, that you can turn off the power of some segments which are not been in use. From the architectural perspective, the folks knows that when this unit is working, this might not work up. When this unit is working, this might not be in the process. So what they do is they do a power gating. This is the main funda. The power gating is the one thing which led to the development of low power designs. Okay. This is one. There is one more which also contributed it, but this is also one of the highest thing which helps the designer to achieve low power. That whenever the power is not been in used, switch it off. Correct?
Yes, ma'am.
Okay. Now comes the third concept, which is also the most famous concept because of which we landed up to like different techniques for low powers. Okay. Now what happens is, if I have to correlate it with an example, let me think of it. Okay. You guys know that I'm not sure if you're really very good with the specifications. When there was 180 nanometer designs and 45 nanometer designs, what was the voltage being used over there? And now when we are in the 2 nanometer, 3 nanometer, what's the kind of voltage being used? You just Google it, okay? Every answer I'm not going to give it. Just look at it, that what was the voltages being used at the longer, older times and now. Okay. The earlier chips, I'll just say that the earlier chips which were being designed, right, they were all working on a complete single VDD. For example, let me say that 1.8 voltage was the one which has been applied. Okay. So all the components in your chip were supposed to get 1.8 volt. Okay. But then the designer thoughts that everything does not require this kind of power, right? Okay, like when Upendra and Venu were running, correct?
Yes, ma'am.
Upendra needed only one
One
this
parle
Parle-G,
biscuit.
while Venu needed two. This is, see, power supply is the kind of energy you give for a device to run, correct? That's the
Yes,
only
ma'am.
source, correct? So for machine it's VDD, for us it is the food. Okay. So now when I can see that Upendra within one voltage, like one Parle-G, he can run for 5 kilometers. And when I'm thinking of Venu, he needs 2 voltages. But earlier, what was this? That no, I have to give 2 volt even to Upendra also, because I didn't have the choice. Now, with the development of these techniques, I am like, okay, I'll have both of this participant in my marathon. I'll give 2 packets to Venu and 1 packet to Upendra. So this helps me to save. See, if earlier I have to give 2 to Venu, 2 to Upendra, it is 4. Now it is
Yes,
now
ma'am.
costing me 2 to Venu and
Three.
1 to Upendra. It's still costing me 3 only, right?
Yes, ma'am.
So that way it happens that why not, for example, if you know the real difference between CPU, GPU, there is like NPU, TPUs, lot of there. But if you know it's a simple difference between CPU and GPU, CPU are relatively slower as compared to the GPU. GPU has to do a lot of calculations in terms of graphics as well. The speed has to be high because they are designed for your gaming purposes, your good quality of video purposes, right? They have to be very faster, correct?
Yes, ma'am.
While the CPU does a
Ma'am.
normal arithmetic calculation, it does not do a wonderful job. Okay, so what happens is, if you look at an SoC and open it up, that if you look into the specifications, CPU does not need a lot of like the requirement for the VDD is low for CPU as compared to the GPU. Okay, so the thing is, the concept kept is like we will use some voltage for some chiplets, we will use something for our different. So there comes this concept of multi VDD. Okay, so this power gating and the multi VDD are the one which helps us to achieve a lot of good improvement in the low power designs. Okay, I'll go quickly because we are running up on the time. The next thing is variable frequency scaling. Okay, you looked into the factor, right? Alpha F C VDD square F, correct? F. Now, as I said, right, everything does not have to be operated at a very faster frequency, right? For example, let's take a very simple example. If you have something in your phone, if you have something as camera, which is to capture pictures, and the same camera, but not to capture pictures, something to do as a video. Okay, now if you look at the specification, video will need a higher frequency because you don't want it to be slow. You want it to be in the perfect pace, right? It should, whenever you are capturing a video, it should not be in a slower pace. While the camera, it can be a bit slower. So the frequency of operation for the camera is lower, while that for the video is faster. So you can play with the frequencies in the design, that which needs higher frequency, I'll give it the higher frequency, which does not need it, I'll keep it at a slower frequency. And the combination of changing your frequency along with your voltage is called as DVFS, which is dynamic voltage and frequency scaling. Okay, fine
Yes,
guys.
ma'am.
This is the techniques. Okay, now you got to understand, like, is there a need for low power designs? Correct? And what are the techniques?
Yes,
Yes,
ma'am.
ma'am.
Guys, are you up? Or you have already zoned out? Please speak it up. Gen Z guys.
Yes,
Going
ma'am.
very fast.
Correct. Okay, so let me now move to the important topic, which is the heart of the discussion, which I wanted to have is the low power design cells in the VLSI. When you have come to something that, okay, you need these techniques to be implemented, you need to have some cells which will do this task, right? On theoretically paper, you have discussed, okay, we want this. But in order to implement in the physical world, there are specially designed cells, okay, which are called as low power cells in VLSI. Okay. Now, when we go to this, now, let me say that the one technique which we discussed was power gating, correct?
Yes, ma'am.
Which is, what is power gating?
Completely turn off the power, ma'am.
Completely turning off the power. Okay. Now, tell me, in order, for example, now a very old school bookish definition, you know what is power? It's like the energy required for the current to flow around the complete circuit. Okay. P is equals to VI, right, guys? This is the
Yes, ma'am.
basic. Even I would have forgotten it. You guys are like still freshers, right? Guys,
Yes, ma'am.
speak it
And
up.
DG
Yes,
upon
ma'am.
DG.
Yes, ma'am. It's correct.
Okay. So now, in order, let's say in order, let's take a very common example. I have said the current to flow, right? Now let me take an example of the water to flow. Have you guys visited any waterfall? Sagar waterfall, which is in the Goa, or any waterfall, Hebenical waterfall in Bangalore? Any guys?
No, ma'am.
No, you have not visited any waterfall?
No, ma'am.
No.
Oh
No,
my God.
ma'am.
No.
Please take a vacation and do go and visit any waterfall. Okay. Actually,
That's
have you
what I job.
seen the picture of waterfall?
Yes,
Not
ma'am.
okay.
Yeah.
If you're not, I've said if you're not visited Las Vegas, it does not mean that you have not seen the photo of Las Vegas. Okay, at least you have seen the photograph of waterfall.
Yes, ma'am.
Okay. From where does the water fall?
From top to bottom.
From top to bottom. Something which is top is considered as something high and bottom is considered something at lower level, correct?
Yes, ma'am.
Mm.
Similarly, how does the current flow?
Higher voltage to lower
From
voltage.
Correct, from a higher voltage to the lower voltage. Okay. Now, when in order to current to flow, you need a difference of voltage, right? Until there is a potential difference, there will be no flow of current, correct?
Yes, ma'am.
Yes.
You need, see, in VLSI terminology, higher voltage is always termed as VDD. Lower
Mm.
voltage, we as a students used to call it as ground. Mostly here
Yes.
they also term it as VSS. Okay, so
Yes,
now
ma'am.
you consider something at a higher voltage is VDD and something
Lower
at a lower
voltage.
voltage is VSS. Okay.
Yes, ma'am.
Okay, so now in order for the complete current flow, you need both VDD and VSS. If any one is missing, there will be no flow of current, right?
Yes, ma'am.
Yes.
I can either remove VDD, I can either remove VSS,
Yes.
correct? So same, because of this, if you either remove VDD, which I said is at higher voltage, correct? Higher means at head. Okay, so there is something power switch which is called as header power switch. Okay, what will it remove? It will cut off your VDD. Okay, and the another terminology which in order to remove your ground or VSS, there is something at lower voltage which is called as footer switch. Okay, understood?
Yes, ma'am.
Yes, ma'am.
Okay, so the power switch is nothing, but it will completely block, or this is a power switch is used for power gating techniques. Okay, you understood? The techniques which I discussed in the power gating is to completely turn off the power. In order to implement that technique, I am using a power switch. It will completely remove either the VDD or the ground from your design. Okay.
Yes, ma'am.
And the types I have discussed is either you can remove VDD, which is header switch. If you remove ground or VSS, this is called as footer switch.
Right.
Okay.
Yes, ma'am.
Guys, are you up and along with me?
Yes,
ma'am.
How many are still have the energy left?
Yes, ma'am.
Ma'am.
Yes, ma'am.
Okay. Now the next cell is very interesting cell. Okay, I won't put up the name directly. I want like to create some good kind of scenario for it. Okay, so that you guys only land up to this. Guys, do you watch Shark Tanks?
Ma'am?
You ever watch
Yes,
Shark
ma'am.
Tanks? Okay, anybody out of you had this like motivation that you also want to present some pitch and have startup and business ideas? Nobody? Really? Gen Z guys? Startup idea does not mean that you have to own a company or something. It can be a very simple startup, man. You never thought of it? I always many time thought that I should have a vada pav stall in Mumbai. Guys, you never had it? I want two people who should have at least this idea. Any two people. Now, because Upendra and Venu have already ran into the marathon, they are tired. I want other two folks. Come up quickly, quickly, quickly.
Yes, ma'am.
One is Piyush, other one. Anyone else along with the Piyush? Piyush can't, this is not Piyush, somebody else along with Piyush. Come up, please, folks. I want how many of you are active. Okay, otherwise, I'll keep on calling one by one's name.
Yes.
So, Abhi, you are there along with Piyush? Man,
Yes,
I'm
ma'am.
not I'm not asking for any funding purpose. Okay, don't be threatened of that ma'am will ask for the funding to start up. Okay, I'll be a seed investor in your. Okay, so Abhi and Piyush, are you ready to take up a startup investment?
Yes, ma'am. Yes, ma'am.
Okay. Now what happens is the Piyush and Abhi, they have a good idea of, for example, that they want to do a startup. Let's say the startup is in VLSI field itself. Okay, they are also planning. Let's also build some organization, a training or institute or something. Okay, so they have also decided we will also make up an organization. Now they just had an idea and everything rough template ready with them. Now, in order to start any such this, you need an investment purpose of lakhs rupees or something that they have a target. Okay, so there is something that there are investors. Okay, guys, you have watched a picture series. There is a TV of pictures which is related to all this fundings or something. Who have motivation in startup? There are good series over there. So do keep on watching. So you have to go and approach to someone who is an investor. Okay, you know this much, at least this terminology.
Yes,
Yes,
ma'am.
ma'am.
Okay, so now Piyush and Abhi are the ones who have their complete pitch ready and they are very enthusiastic and they go in a very good hotel, a 5-star or 7-star hotel in the Bangalore. Okay, a good brewery, and there is an investor which is coming up over there. Okay, now the meeting has started. Now not Ramesh, what is Piyush and this Abhi are presenting their idea, or they just the idea, it's called like they are presenting their pitch. Okay, now since it's a very good brewery and everything, there is lot of good cocktails over there. Okay, now what happens that the Piyush, since he's getting it for free, he started taking up. Okay, now he keeps on taking it up after, like, he presented a pitch for 15 minutes, then he takes it up another glass of vodka, another shot of everything, and he keeps on taking up the cocktails. Okay, now what happens is after 5 shots, Piyush is completely dozed off. Okay. Now in the presentation or while giving up this pitch, what happens is Piyush is stating to the investors, stating like this, our organization of VLSI will be able
Ma'am,
to deliver 500 pizzas to all the politicians who are participating in this rally. Guys, did this make any sense?
No, ma'am.
You are understanding which pitch you are delivering and what he's stating? He's stating that I will deliver 500 pizzas to all the politicians who are participating in this Diwali rally. Nothing made sense, correct?
Yes, ma'am.
Now Abhi is like, this man is completely gone because he has completely dozed off. Okay. Now Abhi has to pitch in, correct?
Yes,
guys,
ma'am.
Guys, you're up,
Yes,
right?
ma'am.
Yes, ma'am.
So Abhi, you have to now, like, because Piyush has completely gone, now you have to take it up and you have to present this like, oh, we will have 250 students with Verilog batches running from this timing, PD batches running from this timing, correct? Guys,
Yes,
understood?
ma'am.
Yes,
Yes,
ma'am.
ma'am.
In this is a very wonderful cell in your design. The main idea behind this is like the Piyush got dozed off. When I correlated with the low power design, It's like the Piyush battery is gone. Okay, he has been power gated or he has been completely switched off. Okay, but he is delivering a pitch to something else, which is to the investor. So let us consider that that is a different block. Okay, now in order that the block should receive a proper signal, okay, a signal in a VLSI means a proper 0 or a proper 1. Okay, we don't deal with any other things, correct? Either it has
Yes,
to be
ma'am.
proper 0 or it has to be a proper 1, correct?
Yes, ma'am.
Yes, ma'am.
Okay, so Abhi pitched in. Okay, Abhi is a kind of a helpful cell. That cell is the second cell which I want to talk about. He's a helpful cell that is allowing to deliver a proper pitch to the investor, correct?
Yes, ma'am.
Okay, now this cell is a very simple cell, and this cell can also be of two types. Okay, the first thing is, you guys tell me if I have to take basic gates on, think of only basic gates. Okay, you know, right? What are the basic gates?
Yes, ma'am.
Now, out of that gates, think of a cell which I want to deliver only one. If I have to deliver at the output of the cell, I want only one. Which cell will you use?
And gate.
Or gate, or gate.
OR gate. Why AND gate? Not or AND gate, it's always OR gate. Because if any of the one input of an OR gate is 1, you'll always get 1 at the output, correct? So you'll use
Yes,
an OR
ma'am.
gate. If you want a 0, what will you use?
And
If you
gate.
want a 0, which gate can you use?
And
And
gate.
AND gate, correct? Because if one of the input of an AND gate is 0, whatever is the other output, it does not matter. Okay, if Abhi is always tied to 0, whatever this, who was the other person? Piyush, whatever bullshit he is speaking, it doesn't matter, correct?
Yes, ma'am.
Abhi will always deliver 0. And if it's an OR gate, Abhi is always 1. Whatever Piyush is speaking, it doesn't matter. Okay? So, this cell in low power design is called as something which is isolation cell. Okay? You got it?
Yes, ma'am.
This is a cell which is mostly and very predominantly used when there was a technique, right? The power gating technique, right? Where power gating techniques was implemented using power switch, but when there are two types of domain, which is like power domain, which is one is on and other is off, this kind of cells are being used. Okay, so that whenever the signal is going from something which is off to on domain, you need the value to be properly tied up to either 1 or 0. Okay, so these are the kind of cells, that is AND cell and an isolation cell. Okay, guys, understood? Am I good with
Yes,
the
ma'am.
examples, or you
Yes,
need
ma'am.
somebody else with the different kind of examples?
Understood, ma'am.
Understood? Correct?
Yes, ma'am.
Okay, now these two guys, because they did a blunder, they lost the pitch. So the investor is not ready to go ahead with this pitch. Okay, because of which person? Because of Piyush, right?
Yes, ma'am.
So now
Yes,
Piyush, you
ma'am.
did a blunder. But I want two other folks. Where are the other folks? How many are there right now? Guys, you're up. Meghna, you're up.
yes, ma'am.
Any other women? Any other lady? Any other young cutie pie over here?
No, ma'am.
Any other girl over here? Along with Meghna, I want a girl. No one else?
Ma'am.
No, no. You're the single girl over here? Okay, man. Okay.
I am also there.
Okay, Sam. Okay, great. So Meghna and Sam is there. Okay. Now, guys, you lost the pitch. And these two ladies have a very brilliant idea. Okay. They have a very good pitch. And they again went to the same hotel and they presented the same pitch. Nobody was dozed off. Okay. They presented it very well. And the finalist, the investor, was very much happy with them. And the investor directly gave them a seed A funding of around, let's say, 10 lakh rupees. Okay. Now, Meghna and Sam, after receiving this, what would you like to do? Receiving such a huge amount of money, wouldn't you like to have? Meghna and Sam, are you not excited after receiving 10 lakh rupees? Sam, where are you? Hello, am I audible?
Hello. Yeah, you're audible, ma'am.
Okay. So after receiving this amount, Meghna and Sam decided, let's have a party. Okay. So now they go on a dance floor. There is a good dance floor over there, along with the investor. Okay. Now they go on the dance floor. Now on the dance floor, there is a very huge, loud music. Okay. Now, meanwhile, they were dancing, the investor got to know, okay, man, I didn't took up the mail ID of Meghna. Okay. I wanted to take up because she's the founder and Sam is the co-founder. Okay. So they wanted to take up the email ID so that they can send up the relevant documents. Okay. There is a very loud music over there. Okay. Now Meghna is very soft spoken person. And she replies stating that it's Meghna at the rate VLSI Foundation, something. She speaks up like MEGH. Okay. But what happens that the investor cannot listen in such a loud music, and the way, because the Meghna is very soft spoken, she is not able to higher up her or amplify her voice. So Sam comes and pitches them. So whenever Meghna says in a very soft voice, it's like MEG, Sam comes up and say that MEG. Guys, understood? She's doing the amplification task. Okay. The
Yes.
third cell is also similar kind of a cell, which does a similar task in your VLSI design, and that is called as level shifter cell. The way Sam amplified her voice, it also shifts the level. It shifts the level of the voltage. Okay. So what it does it, whenever there, because I said, right, you heard a concept in the techniques, there was multi VDD. I said, right, multi VDD means you're operating on the different voltages. Okay, one is operating on 0.8 volt, one is operating on 1.2 volt. So what happens is whenever the signal goes from different voltage domains, they need to be leveled up. Either need to be leveled up. L to H means whenever it's going from low to high, you need to boost it up, or when it's going from high to low, you need to lower it down. Along with this, now earlier it used to be two different kind of a cells. Now they have designed up in such an efficient way that the single cell can be used to go by level. It does the job of both high to low and low to high. Okay, guys,
Yes,
understood?
ma'am.
Yes, ma'am.
Yes.
These were the three. As of now, there are different cells as well. There is a retention cell, there is an always on buffer. But my main intention to cover up in this was these three cells. Okay,
Yes, ma'am.
you got it? So the first cell which we discussed is the power switch cells, which completely shut down the power supply. Okay. So now the way it looks is, for example, this is a complete block. Okay. This I have mentioned as power gated block. I said the word gated means which can be turned on or off. So this can be turned off. Okay. And this is which in a different kind of a grayish shade is an always on block. Okay. So now this power switches have to be placed at the entry point, right? This is the controlling point. Whenever I will send a signal either to turn off VDD, it can turn off the VDD. I may send a signal to turn off the VSS, so it will turn off the ground supply. This is just a black box which I have drawn because I'm not going into the deep internal designing and the structure of the power switches cell. This is very simple. You can Google it after the lecture that the header and the footer switches are nothing but your PMOS and NMOS. They are not CMOS, they are PMOS and NMOS. Okay. So
Yes,
like
ma'am.
when to use it, that when you know that in your design you want to turn off some domains, you can do it using this power switches. Okay, switches like turning on and off. I want to give the power, I don't want to give the power. Okay, the next we discussed is this header switch and the footer switch. I said, right, it's purely PMOS and NMOS. You go and deep dive into it because the motive of this lecture is not internal. I'm not going to explain in detail, but you can look at it. Okay, the second cell is the isolation cell, right? That you want to clamp the value, even if the signal is coming from some off domain and going to some which is on, we don't know. The value can't be predicted. And in VLSI, if a value can't be predicted, it goes to a metastable state that we are unaware. So this is not something which is good. Okay, we want either it has to be proper 0 or a proper 1. Okay. So see, in this kind, if you look at it, the signal is going from this is a gated domain, correct? Because I have used a power switch. Okay. If you look over here, this is a switch. So this can be turned on or off. The signal is going. In case this has been turned off, the signal is useless. Okay. So you need a signal to come it up, which is like in our case, the person who was handling up the pitch after Piyush, right? Abhi. So this is the isolation signal. Okay. And this has to be placed. See, isolation cell has to be placed in the domain which is turned on. I have not placed it somewhere here. Okay. If you look the placement of the cell, if you go, I'll explain in the forward lectures. Like if you look at the UPF, the placement of the cells are also the strategies which has to be decided, right? For example, if this cell is itself in the power of domain, then how will this cell work, right? If Abhi also get drinks up and he also loses his control, then there is no use, right? He has to never drink it, right? So that's why this has to be placed in always on domain, not in somebody who can be gated up. Understood?
Yes, ma'am.
Yes.
Yes, ma'am.
Whenever the signal is going from an off domain to a on domain. See, look at whenever a signal is going from a off domain to on domain, you need it. Okay. The terminology over here is it's not purely off to on. It is termed as less on domain to more on domain. Okay. Okay. And the next is we discuss the type that it can be either or and. And the third one which we looked upon was the level shifter cells, right?
Yes, ma'am.
Whenever there is multi-VDD designs, you want to level up or level down your signals. So see, PD stands for power domain. So this is operating on a different power domain. The other design is operating on a different power domain, correct? So you need to shift up the level, whether it's going from high to low, low to high. Okay. Over here, you can see like it's going from 0.8 volt to 1 volt. So you need to convert to low to high. Whenever signal is going from 1 volt to 0.8 volt, you have to convert high to low. You got it?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
So where are these placed, ma'am?
These are placed in the designs. For example, let me come up with an example. Okay. Guys, you can see an example over here. I have this is the final slide which I want to showcase you. Okay. Now you guys have to answer me. This is something I can't answer it. Okay. This is something your answers will tell me that how much I have delivered has gone in your head. Okay. Guys, be proactive now. Now
Yes.
tell me. I am not sure. Okay, I'm not sure if I can. If you can look, there is a design A on the left side, design B on the right side. Design A is operating on 0.8 volt. Design B is also operating on 0.8 volt. Design A, I have mentioned, is at always on. Can you look at it? This device
Yes, ma'am.
Yes,
will
ma'am.
always be up. It will never go down. Okay. But design B, I have stated this as power gated, correct?
Yes, ma'am.
Okay, power gated means you understand?
Completely turn on.
It can be it can be turned off. Okay.
Yes, ma'am.
Now the third is this one, design C, which is within a design A. Okay. But the operating voltage of design C is how much?
1.2.
1.2 volt.
1.2.
Okay. Now there are signals which are crossing up. Now let me tell you what is PMU. PMU stands for Power Management Unit. Whatever this I explained you, all this kind of a cells, right? There is a UPF, which is called as a Unified Power Format. Okay. These are these strategies I have explained you in a very layman language in order to explain to the system, in order to explain it to our ICC2 tool or your Synopsys or Cadence tool. You have to write it in a language, right? The UPF is that language. Okay,
Yes,
it
ma'am.
defines where should be the placement of the cells. Either whether I should use a header switch or footer switch, whether I should use AND isolation or isolations. How will this signal come from? Okay. So this is completely controlled by this PMU. And if you look, the PMU is always placed in which domain? Always on domain. Because if this person who is giving the command and controlling it is in a power gated domain, what will happen? If the power goes off, it can't control everything, right?
Yes, ma'am.
So this PMU has to be placed in the always on domain. Okay. Now just explain me, for example, a signal is going from this logic, which is in design A, to logic, which is in design B. What cell has to be used in this A?
Switch.
Out of I have given example considering only those three cells. Okay. Now just tell me.
Isolation
Power
cell.
switch.
Oh, somebody said isolation or somebody said power cell, correct? Now just think
Yes.
upon it. Why power cell? See, the power cell is cell which is something which is used to control the power gating. Okay. The power cell will not be placed something in with my annotation. Okay. Something from example, if there is a VDD over there, let us consume that this is a VDD rail. Okay. This is a VDD rail for 0.8 volt. Okay. Now this VDD is going over here. I'm very bad at drawing. Okay. This is going over here. But in order to go over here, there has to be power switch at here, which controls this. Okay. If this is the switch, this will either give a signal whether to turn it on or off. Okay. This logic, sending the signal to this logic does not have to do anything with the power switch, right? Because it is not sending power. It is sending some signals, correct?
Yes, ma'am.
Yes.
The power switches will never be included for the signals which are traversing within the design. This is something at when you're doing at a power planning or something, and there is a way this switches are being, there is a daisy chain fashion in which these are being implemented. So these are implemented at top level. Whenever the signals are going over across the domains or within the logics, power switches can't play any role because they are not sending powers, they are sending the signals. Okay. So now somebody else said which cell has to be used. Now we have ruled out the possibility of power switch. Now somebody said isolation cell, correct? Who
Yes.
said isolation cell?
Yeah, Mridula. So you're asking from always on to power gated, right?
Yeah, I'm asking from signal which is being traversing from always on to power gated. This is a signal.
Okay. Nothing is needed, I guess.
Nothing is needed.
Yeah, nothing is needed.
And can you just give me an explanation why nothing is needed? One is on, one is off. Why there is there is no
Yeah,
any
if
cell?
it is off, if it is off, right, it doesn't care what signal it's coming in, right?
So the thing is, right, whenever I explained you this kind of isolation cell, I stated it's not always off to on. I gave you a terminology stating whenever a signal is crossing from less on to more on. Okay. The less on to more on. Okay. Now my this block design A is always on, which is means it is most of the time it is on. Okay. And this is going to a off domain, correct?
Yes, ma'am.
Okay, so this does not require any cell. When when the signal is going from less on to more on, that time only you need the thing. For example, if somebody is sleeping and you are delivering something, it does not need any kind of thing, right? Because the other person is sleeping. While you are on the receiving end and you need a proper information and the other person is sleeping and saying anything, you can't get it because you are on, correct?
Yes, ma'am.
So always remember that the isolation cell is required whenever a signal is going from less on to more on domain. Okay. Understood? So
Understood.
A1 does not require any cell. Okay. Guys, understood?
Yes, ma'am.
Yes, ma'am.
Now A2. Guys, answer it. I want
Isolation cell.
isolations. Now because
Yeah.
isolation is needed because the signal is going from less on to more on because design B is power gated means it is off. It can be off. When B is off, A is still on. So you need an isolation cell so that it does not receive any metastable value. It does not lead to metastable condition. It does not receive any random value. Okay.
Hmm.
Now let me now about instead of A3, A4, let me come to something as A5, A6. Let's go. A5. Guys,
Nothing
Isolation.
is required.
On.
Level shifter is required.
level shifter is required.
Yes,
The,
because your voltage difference is there, right?
correct. Because the logic which is sitting in design A is operating on which voltage? 0.8, correct?
0.8.
Correct. And now you want it?
Level shifters.
Yes. Now which level shifter? I discussed two categories. Guys, which category? I discussed two
Low to
categories.
high.
Low to high, correct? Very simple because it's going from 0.8 volt to
1.2.
1.2 volt.
correct. So you need only this. You don't need an isolation cell because again, you are going from more on to less on. You don't require it. Now think of A6.
Ma'am, isolation.
Isolation
From
because you
high
are
to
going
low.
from
High to low.
High to low level shifter.
okay. So this time you require two cells. Okay, you even need a high to low level shifter and you need an isolation cell. Okay, got it? Anybody have any doubt? You can ask me. This is
Yes,
a very
ma'am.
simple example. Okay, now let's go to A3. Now,
I'm
okay,
only level shifters.
only level shifters. Now
Yes,
you
ma'am.
have to ask me a question. Ma'am, you have mentioned both the design B and the design C are mentioned as power gated. Which one is more on? Correct? The specifier, the one who designs this architectural perspective knows it, okay? So the question arises that when you're writing UPF, you want to know which one is the more on. Now let me say that design B is now more on. This is a more on design, okay? This is more on. As compared to, both are power gated, but for example, let's say very layman language, I'll say that for 10 minutes this device is working. Out of this is on for 8 minutes. This is on for just 5 minutes. So what you came to know that this is most of the times this is more on, correct?
Yes, ma'am.
And this is less time on. So now
Mm.
you can think of whether you need isolation cell or not. Let's
I mean,
A3.
in
We
A3, ma'am, we need
don't need.
isolation. No, we
No,
don't
we
need
don't
isolation.
need.
Just
You
need
need isolation
level
or you don't?
shifter.
Okay,
And we
A3 you
don't
only
need
need
that.
level shifter.
Yes, ma'am.
And which kind of level shifter?
Low to high.
Low to high. You don't need isolation cell, correct? Why?
And because we are
Because
going
B is
from
more
low level
on.
to high
Because
level,
we are
and
going from more on to less on, and there is no requirement. Whenever we are going from less on to more on, you require isolation cell. Now think of A4.
isolation and level shifter.
Correct. Here you will require more isolation than the level shifter. Correct? Now you guys are well versed with these three cells, right? There are different lot of cells. There is a retention cells. I said there are always on buffers, but I could not complete in this time frame. I have already extended this time frame. But the complete UPF, and I'll teach you the complete UPF. This arrow very simply stated where can I keep these cells. There is a complete strategy to define this thing, right? Whether this cell which I'm placing over here has to be placed at this side, or I can place it over here, or I can place it over here. Okay, there are some combinations which are proper, there are some combinations which are not proper, correct? For example, if you have mentioned that your isolation cell, let's say here, what was, I'll just give you one example. A2, you said you need isolation cell, correct?
Yes, ma'am.
Now what happens if I keep an isolation cell over here? Let's say that I am clamping this value. This is something which is coming up from here. This is my isolation signal. Okay, this isolation signal comes from this PMU logic I said, right? This
Mm.
isolation cell is over here. Now I have placed it over here. Think logically. Is the placement correct? See, when you are looking at a cell, you always forget that it always have a power ground pin, okay? It has VDD and ground as well. You always look. Now, since this is an always on domain, it will get the power, correct?
Yes.
Yes, ma'am.
But for example, if by mistake, I know that this signal needs an isolation cell, but I place this cell over here. Okay, still getting this one. And now this signal has been traversed from here. Logically, if you look, you are still using the proper cell and the proper signal, correct? The signal is going, it needs an isolation. I kept an isolation cell. It is getting an isolation signal from PMU unit. But what happens is about VDD and ground. Because
Yes.
already this design B is not operating, means it does not have, this cell is useless, correct? It's not getting the
Mm.
power. It cannot perform its task for which it has been intended, correct?
Yes.
So you need, this is completely, the complete UPF is itself is a very vast topic where you need to decide and define the strategies where it has to be felt, whether it has to be in the child block, parent block. That is very, very deep. This was my overall understanding about what are the different types of low power cells which are there in the design. Okay.
Okay.
Okay. Anyone else? I have concluded the lectures from my end. I know that your battery would have gone down because you just had breakfast. Your energy was already down 2 hours back. You now need to go rush for lunch, okay? So anybody, any questions from your end?
No, ma'am.
Anyone? Hope you had a great time with me.
Yes, ma'am. Yes, ma'am.
Wait, can I stop sharing?
Okay.
Okay, I'm not sure who is the host right now.
Ma'am, me.
I
Yes.
think Piyush is the host, right?
Yes, ma'am.
So can I conclude the lecture?
Yes, ma'am.
Oh, okay, great. Thank you so much, everyone.
Thanks, ma'am.
Hello.
Like,
Thank you.
Hi.
what's the
Thank you.
best
Hello.
lecture?
Oh, no issues. Thank you.
Hello, Mridula. Hello.
Yeah, hello.
Yeah. So Mridula, one question I have. So from here onwards, so will we have a follow-up sessions or it was just a demo class, or I mean, just wanted to know if we will have a follow-up sessions or not from here onwards.
You can reach out to the owner of your VLSI for all. He might update you.
Okay, sure.
Yeah.
Okay. Could you
Okay.
please share the PPT?
Oh, you guys want the PPT as well?
Yes, ma'am.
Okay, I'll check with this. I think Rajat, right? I'll
Yes,
check
ma'am.
with Rajat and share it over his mail ID. Okay, guys.
Okay,
Anything
thank
else?
you.
Okay,
Any
ma'am. Thank you, ma'am.
questions
Have
regarding
a
anything?
nice day, ma'am.
You too, guys. Keep up your energy up. Don't be like a leakier device. You are Gen Zs. We are millennials. So keep up your energy high, your spirit high. Your battery life has to be longer, just like the design which we made it right now. Okay.
Okay.
Thank
Yes,
you.
ma'am.
Okay. Chalo. Then bye bye. Have a good day.
Same
Bye,
to you,
ma'am.
ma'am. Bye.
Yeah. Bye bye.